Good morning, dear student, and welcome to this 29th edition of our Numerical Method 2 class. Welcome, Johannes. Okay, without any further ado, I will quickly recall what we did last time during our last class. So, in our last class, we covered what we call the recursive trapezoidal rule. Trapezoidal rule for equally spaced subinterval. Equally spaced because our xk can be written as a plus kh, where h is the step size, constant, right? And h is b minus a by 2 to the n. So meaning that the number of subinterval is a power of n, right? So for the recursive trapezoidal rule, we use this rule, this formula. This is what we use, but we use t instead, right? T, we call it tj. T just to indicate that they are all trapezoidal rule. So what we did, we used that rule to compute. We apply it. We apply it to this particular problem. Let me quickly share the slide of what we did last time. So last time, this is the problem that we solved. We apply that rule to this particular problem, right? And I think that by now, each one of you should be able to do that. So this is the form of the recursive trapezoidal rule that we used. We use this form equally spaced because you can see that our x sub k is a plus kh, where h is the step size, right? With a power of, 2 to the power of j is the number of subdivision, right? And now the number of summation here is given by capital N, which is 2 to the j minus 1, right? This minus 1 is not 2n minus 1, but it's 2j, sorry. What I mean is that here, n is 2 to the j minus 1. And this is different. It's different to 2 to the j minus 1, like this. You can see that this is odd, whereas this is even. Right? Because this is a power of 2, so it's an even number. Whereas this one would be an odd number. So it's not this one, but it's this one instead. So it's good to stress on that. So what I want to draw your attention on is that in this summation, you only have the interior point. There's no end point. The endpoints are all kept inside here. You can see that you have f of a plus f of b. So the endpoint a and b are in T0, and they will be used here all the time because we'll be dividing this by 2 all the time. So this T0 will be divided by 2 to give the new one divided by 2. And to this interior point, to this end point, these are the interior points that will be added. So the interior points are kept into this summation, but the end points, f of a, f of b, are all kept inside this first term that will be halving each time. So they are here. They are all kept here. So don't think that f of a, f of b are not computed. They are already in this. We have that each time. And here we only update the interior point because the interior point will be changed, but the end point you still have f of a, f of b. But because h is being halved each time, that's what we are doing here. We halve also this each time. So you see that it makes the formula to be consistent. Okay, so for j equal to 0, 1, 2, 3, these are the procedures. So you have the procedure how to compute the summation and how we have this part. So this is how you apply this formula, and it's very important for you to master this procedure. You have to do it. Good. Okay, so we only stop here. That is, if we are to draw a table, it's as if we fill the first column. Now we are going to see how to fill the rest of the column, because remember that we are trying to improve the computation by drawing a table. However, you have the first column here. You have the first column that gives you the trapezoidal rule, and then you have the remaining columns. And so forth, depending on how. Okay, so here, this first column is when j is equal to 0. So here, maybe I can add another. Okay, so let's say that this is k equal to 0. So this is k equal to 0, k equal to 1, k equal to 2, and so forth. So this is k, and we know that when k is equal to 0, you have t, tj. Now here j is equal to 1. J equal to 1, you fill this, and then j equal to 2. And so forth. Okay, so now you see that when k is equal to 0 here, this is our tj, right? Here we have tj when k is equal to 0, because if you recall, we say that r, if you say r when it's a rn 0 is what we call tn, right? If you put j here, it will be tj. So when the column, this is a row and this is a column. So when the column here is 0, so j is n right here. Or if you want, this is our tj, if you want to compare with the other one. So here, this gives us a trapezoidal rule. If you recall, you have the trapezoidal rule here. But we are going to use for the trapezoidal rule, we are going to use the recursive trapezoidal rule. for this one to fill this. So we can call this the recursive trapezoidal. That is the recursive trapezoidal. So that's what we have here. So in other words, we can call it this T1. Oh, we could have even started from 0 instead of 1. We start from 0. Sorry for that. So we start with 0 and then 1, 2, 3, and so forth. So here we have T0, which is in fact what we call R00, right? So this is the same as R00. And then we have our T1, T2, T3. So this is what we computed in the tutorial. So in the tutorial, this is what we did. We computed this column. Now we are going to see how to complete and do the other one, because here we are in the recursive, right? We're using the recursive. Now, using the recursive, how do we fill the remaining columns? So here, here, and there, and so forth. So that is exactly what we are going to do here. That's what we are going to look at today. So last week, in the last class, we filled the first column. This one, the T's. This is what we computed. So the recursive formula allows us to fill the first column. Now, today we are going to see what we call the Romberg technique, right? The Romberg technique to fill the remaining here, here, and there. So that's what we are going to look at today. Now that we have set the stage, let us look at the actual with the Romberg algorithm. So here, this is exactly our TJ that I was talking about, the first column, this one. You can see that here, K is equal to 0. If you look at the column number, is 0 all over. You can see here. So here, this is our this column is our TJ. This one. Now, how do we fill the remaining column? That is when K is equal to 1, K equal to 2, 3, and so forth. Now you see that by so doing, we construct a lower triangular table, right? It's a lower triangular table because here you have R00, R11, 22, 33, up to NN. There is nothing above the diagonal. It's only the diagonal and the element below the diagonal. So that is a lower diagonal. So the lower diagonal part of the table will be filled and the upper will be empty. All right. Now, so this is the approach. Right? And this is still based. Let me remind you. Let me remind you of this. This, if you look carefully, you will see that this is still based on our Romberg technique. Okay, so you can see that this is still based on our technique. This one, if you look at this one, This is our beta estimation. This is the beta estimation we are looking for. This is the more accurate. This is the more accurate minus less accurate, if you remember. Why is this less accurate? So if you look at the raw number here, let's say for instance, we want to obtain this result. So this one, how would we get this one? We get this by fixing the row number, which is n. You can see that we have the same n, but I take the previous column, which is this one. Same row, but the previous column. So it's this one, which is this one. But you can see that this one is the better approximation compared to this one, because we move from R00 to R10 by halving. So this gives us a better approximation. And the one above is less accurate, or less, yes, this is less accurate because the step size for R00 is double the step size of R10. So you see that it's exactly the same principle that we are applying here. But now, why are we getting 4 to the m instead of 2 to the m? Simply because we are halving. Or to put it anyway, let's even put it in a better way. Let me explain it with this. We saw that this n, we said that it's the order of accuracy. So it is this one, h to that power. That's what we put here, h to the n. Now, if you come here, what do you realize? That for the trapezoidal rule, this is what we have. But now when we perform the recursion, we are moving to this. So we move from here to there. And from here to there. So you can see that the next term here is double of this. Right? So it's a multiple, if you want. It's 2 times. It's a multiple of this one. It's 2 times. It's 2 times alpha, if you want. 2 times alpha. So if and this one is a factor of this one. So it's in fact, if you can say, it's 2m, if you want. 2m. So from here to there, m is 0, sorry, m is 1 when we are here. M is 1. And alpha is 2. Alpha is 2. We know that alpha is 2. So in fact, this is 2 alpha if you want. It's 2 alpha, alpha m. It is alpha times m. Now, so this is alpha, which is 2. Now, when we take m equal to 1, we are here. Now, if m is equal to 2, we are here. If m is equal to 3, we are here. You see? 2, 4, 6. Right? Now, so here we will write 2 alpha, or m alpha if you want. But alpha is 2 for the trapezoidal rule, alpha is 2. So we replace n with 2m. So n is equal to 2m. Now, if I come here, I write 2 to the n minus 1. But since n is 2m, it will become 2 to the 2n. 2, I know that 2 to the 2m is equal to 2, right? This is elementary algebra, which is 4m. So this is 4m minus 1. So that is why we have this. So it's exactly the same. It's still our Romberg. It's this one. It's still this formula we are using. So don't think that is something new. It's exactly this. The same thing. All right, so, okay, so that's how we will compute the remaining columns using the Romberg or the Richardson technique, extrapolation technique. So that is the same thing. To get the next column, the entries of the next column in terms of the entries of the previous column, because remember, to get an entry here, I will use the entry in the previous column, in the current row, and the row above, or the previous row. That's exactly what we are doing here. You can see that we are using the same row. We use the same row, and then the previous row, right? So we have you see, sorry, Rn, so we have n here, and then n minus 1 for the one above, for this row, but in the same column, which is the previous column. So if you look at the column number, you see that it's m minus 1, m minus 1, m minus 1. So if the column is m, all of our computation is done in the previous column, m minus 1, m minus 1, m minus 1. So to fill this entry, I use the previous row, the previous column. And in the previous column, which is m minus 1, m minus 1, m minus 1, I use the current row and the previous row. The current row, which is the n, and the previous row, which is n minus 1. N minus 1. So we have n and n minus 1. N and n minus 1. Okay, so this is for your understanding that I'm doing this. But this can still be rearranged. This can be rearranged. Because you realize that in some formula, you will not see it in this form. It will be written in a different form. Because if you look at this one, what is it? Like here. Okay, let me write it. Let me write it somewhere else. Okay, let me do this. Then we come here. Oh, sorry. Okay, so let me do this. So we are here. So let's say that you are here. This is R, N, M. Right? This is what I want to compute. So the column here is M. So it's a M column. Now I know that in order to compute this, I will need the previous column. So meaning that in order to compute that, I will need this column, the M minus third column. This is what I will be using. I will use the current row and the previous one. So I will use R, same row, right? The same row, but previous column, which is M minus 1. Now, the previous row are N minus 1, M minus 1 in the same column. So I use these two to compute this new one. So in other words, if you use the Romberg or the Richardson technique to compute this, we know that it will be the better accuracy or more accurate, right? The more accurate. So what is the more accurate here? Is this one. Why is it more accurate? Because h here is the previous h by 2. So if this is, for instance, h, this will be h by 2 because I'm halving. So this is a better accurate, right? This one has a better accuracy. So that will be n minus 1, right? Plus, we know already 1 by 4 to the n minus 1 into, I copy this, right? Because this one, we know already that this gives us a better accuracy or more accurate, right? This is more accurate. This is more accurate minus the less accurate. We know that, right? This one is less accurate. Okay, so let me do this. To get better results, yeah. Okay, but I still need to modify this because, okay, minus this one on top, that will be n minus 1 here. So that will be minus n minus 1, m minus 1. Okay, so that's what we had there. So I'm just writing for you to remember the formula, not to memorize. You just take this there and this one, and then you take this equal to this plus this ratio, this minus the one above, which is less accurate. So that's how you remember the formula. You don't really need to memorize. If you can just remember, you just see the technique, how you construct this from these two. That is it. So you'll be able to write that all the time. You don't really need to memorize. Okay, now what I was saying is that this is the formula that I wrote there, but it can come in different flavor. So you can see that you can cross multiply and take the same denominator. So if you do that, what do you get, right? So because if you see that, don't say that it's a new formula. So that's why I'm taking all the time to write this. So you see that if I cross multiply this and add to this term, so this one will be added to that. And if I cross multiply and add this to that, to this one, we see that the negative one here will cancel out with this one, right? Okay, let me write everything. So if I cross multiply and add to this one, the numerator will become what? 4 to the m minus 1 r n m minus 1 plus, I will add the numerator, that is plus Rn, comma, m minus 1 minus R n minus 1, comma, m minus 1. Or by what? By the same denominator, which is 4 to the m minus 1. So if I expand this, because you see, you agree with me that this one is 4 to the m R n, comma, m minus 1, and then minus R n, comma, m minus 1. So you see, and you agree with me, you don't need a revelation to see it. You just need to, you have your eyes open. Cancel like that. You see, you cancel out this and this, break this into 2. Now you see that you have 2 terms now. You have first one times a factor of 4 to the n minus this one. So which gives us the simple formula, which is in fact a weighted sum, right? 4 to the m into R n, comma, m minus 1, right? Minus 1. You see, the factor of this is 1, right? 1 into, just write, R n minus 1, comma, m minus 1 by you see, I just take the weighted sum. The factor of this 4 to the m and the factor of this negative 1. So I divide by the weighted sum, which is exactly this. So by 4 so you can see that the factor, this one is this factor here. And this one is this. So you see that we have a weighted sum of these two. So in other words, this is a weighted sum of these two. So I repeat, this is a weighted sum of these two, where the factor of the row above is 1, and the factor here is 2 to the n. So I have 1 as a factor here. I repeat, here I have a factor of 1, and here I have a factor of 4 to the n. So if I take this weighted sum, right? So this one will be called a weighted average of these two. Weighted average. You know that if you take a weighted average, you need to know the weight of each terms in the estimation. So the row above, the weight is 1. The row below, the weight is 4 to the n. So I can write that this is weighted average of these two. So it's a weighted average. And the weight, we have 1 and 4 to the 1. So that's what we have there. When you say weighted average, it means that you divide by, when you say average, you divide by. So when you say weighted average, you take the weight, you add them up. Sorry, the weight here is negative 1, negative 1. Right. So I add the weight, so which is this one. Right. Okay, so this is the easiest formula that should be used instead of this one, because this one is a bit longer, right, compared to this one. Just take a weighted average. So it's the same thing. It's up to you to decide which one to use. But I'll just show you that if you see this in some code or in some formula, don't think that they are different. They are exactly the same. So that's what I wanted you to see. Okay, back now to our notes. Go back to the notes. Because we are not yet done. We are not yet done. Okay, so this is the formula. Now, this is just a simple application, right? Now, we are given R42 and R32. We want to compute R43. So just M, you can see that here M is, N is, this is the value of N is 4, and M is 3. So 4, 3. In order to get that, we need M minus 1, which is 2. So this will be R42. And we will need R32 also, which will be this one. 3, because 4 minus 1, 3. 3 minus 1, 2. 3, 2, which is this one. And they are given. Just substitute there in the formula, we get this result. Right, good. So that is an application. So we assume that these two rows, these two entries in the previous row, that is row 2, were computed. So we assume that, as you can see here, is 2, 2. So we assume that these two are known. What is it? 3, 2, and 4, 2. 3, 2, this one, 3, 2, and the next one, 4, 2. And we compute the next one, which is 4, 3. Right? That's what we are using. So 2's in the same columns are given, and then we compute the next one in the next row, in the next column, but of the lower row. Okay, so that is it. Now an application. Application here, you are asked to find an approximation of pi by using the Rhombach algorithm when n is equal to 5 to obtain a numerical approximation for the integral. So this is the integral we want to compute. Right. We know the antiderivative of this one, right? You know that the antiderivative of this is what? Inverse, the tangent inverse, right? And now, because you have 4 here as a factor, so let me write, so this is 4, right? From your calculus into, or the 10 inverse, of 1. Because 10 inverse of 0 is 0, right? So because it will be at 1 minus at 0 is 0, so this is what you're left with. But I know that 10 inverse of 1, that is the angle for which the 10 is 1, is pi by 4. If I take pi by 4, I compute the 10 of that. The cosine of pi by 4 is equal to the sine of pi by 4, which is square root of 2 by 2, huh? If I'm not mistaken. Yeah, it should be that. Now, if you take the ratio, it gives you what? It's pi by 4 anyway. So this is pi by 4. So that would be 4 into pi by 4. Now, so, and this is pi. So the exact value, if you take the antiderivative of the exact value of this integral is pi, which means that if I use a numerical formula, what we call numerical quadrature formula, to approximate this integral, it will give us an approximation of pi. That's how you should understand it. It comes from there. The exact value of this integral is pi. So if I use a numerical technique to approximate this, I am approximating pi. I'm approximating pi. So that is how, when you see, you take your calculator, you press pi, and it gives you an approximation. It's not witchcraft. My colleague, what they use? What did they use? That is it. So something that you know that it will converge to pi exactly. You approximate that thing, it will give you an approximation of pi. If you have a good approximation of that quantity, it will give you a good approximation of pi. All right. Now, we are going to use, obviously, this Romberg technique or Romberg algorithm. And that is it. Now, I would advise you to go through the code. It's given for free for Mahala. I didn't ask you a cent. I gave it to you for free for Mahala. Okay, so what I will ask you to do, this is a MATLAB code. Take this code, write it down, run it, and make sure that you get exactly this value. It will help you to understand the procedure. I'm advising you to do that. Write it, try to understand what it's doing. But after that, that's not enough. Because I encourage you to learn Python, now convert this into a Python code, because this is MATLAB. By so doing, you'll be learning Python at the same time. Use all the resources available. Go to Google, or YouTube, whatsoever. Try to convert this into Python. Because if you copy this verbatim, run it, you will get this. Try to understand the code, right? That was exactly this, exactly this. Obviously, with the new formula that I wrote, because if you look at this, you can see that it's using the weighted average. You can see that it takes this and multiply by 2 to the 4 to the something, minus 1, and you have that ratio here. So this is the second formula that I wrote, right? It doesn't use this one. It doesn't use this. But it uses the weighted average. That is, you cross multiply, cancel out like terms, and rearrange. So that's what you have here. The second formula, that's what you have here. So, and for the sum, I already told you how to compute the sum. When you have a summation somewhere, you take that sum to be 0, and you write something of this form. Sum is equal to sum, and then plus what you want to add. So that it appears here, right? You have it there. So when you are done with the sum, then you can come and write this, right? So please go read this, try to understand, convert this into Python. Homework. Python's function. Okay, so that's the homework. I think I will stop here. Tomorrow we will continue with the Gaussian quadrature formula. Right? We will see that there's another way to look at integral by using a few terms. I think, yeah. So we are left with how many pages? So this is 1, 2, 3, 4. Yeah. So I hope we'll be able to cover that tomorrow. But even if we don't cover, we see up tomorrow, then Wednesday. By Friday, anyway, we should be done. By Friday, we'll cover everything. Okay, I think I will stop here. But I encourage you, as you look at what we did today, you can also read this quadrature Gaussian quadrature rule. Try to read and prepare for tomorrow. Is there any question? Guys, you have the floor. Is there any question? Yes, Guy, I'm listening to you. Is there any question? Frida.
No questions, sir.
Yes?
No questions, sir.
All right, all right. So far, so good.
Yes, sir.
Great, 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 great. Good. Have a blessed day. See you tomorrow.
Likewise,
Bye-bye.
sir. Bye.
Tata. Tata.